The cosmos spoke its first words in total darkness. Long before any star flickered to life, the universe was already shaping its destiny through an invisible force, magnetism. You will gain a completely new understanding of how everything came to be, seeing the cosmos not as a story that began with light, but with a hidden magnetic conversation. How did silent magnetic whispers draw the blueprints for galaxies, and what fossil traces of that ancient language might still linger in the void around us? What does it mean that our universe had a voice before it ever had a face? This darkness was not an empty void but a seething ocean of raw potential. The entire cosmos was compressed into a hot, dense plasma, a chaotic soup where particles of light, called photons, were constantly born and immediately absorbed. In this frantic state, light could not travel freely. It was trapped, bouncing from one particle to another in a blinding fog. Yet within this churning sea, something else was stirring. Charged particles, the building blocks of all matter, were in constant, frenzied motion. And every time an electrically charged particle moves, it creates a tiny magnetic ripple. Think of it like a single drop of water falling into a still pond. Now imagine a trillion such drops falling every second into a cosmic ocean. That was the universe's first magnetic field, a turbulent, chaotic web of force woven directly into the expanding fabric of spacetime. This primordial magnetism was incredibly weak by today's standards, a faint whisper against the roar of creation, but it was everywhere and it was persistent. It acted as a subtle sculptor in the dark, gently guiding the way matter began to clump together. These tiny magnetic ripples created a preferred direction, a hidden grain in the cosmic wood, making it easier for matter to gather along certain lines of force. So even before gravity had finished its grand designs, this magnetic hum was already drawing the faint, invisible blueprints for everything to come. The universe was learning to structure itself in the silence. Those faint magnetic ripples were not destined to remain whispers. Deep within the churning plasma, a powerful cosmic engine was starting up. This is the Dynamo effect, a fundamental process where the motion of a conductive fluid can amplify a magnetic field. The entire early universe was that conductive fluid, a seething, expanding ocean of charged particles. Every swirl and eddy in this primordial soup acted like a turbine in a vast power plant. The kinetic energy of the universe's own violent motion was being harvested and converted, pumping strength into those initial, feeble magnetic fields. It was not a gentle strengthening, it was a runaway reaction, a feedback loop of cosmic proportions. Think of stirring a cup of coffee with a spoon. Your spoon's motion creates a swirl. Now imagine if that swirl itself generated a force that made your arms stir even faster and more efficiently. That is the essence of the dynamo, a self-reinforcing cycle where motion begets magnetism, and that magnetism in turn organizes the motion, leading to an exponential surge in power. The universe was learning to project its voice, using the raw energy of its own birth pangs to turn a murmur into a roar. This foundational amplification did not just make the magnetic fields stronger. It gave them structure and coherence, weaving lines of magnetic force into the very fabric of the expanding cosmos. These newly fortified fields were now potent enough to guide the flow of matter on a grand scale, setting the stage for magnetism to become a master architect in the darkness. But that dynamo needed a seed to amplify. Where did that very first magnetic whisper come from? It might have been born from a crack in the cosmos itself. As the young universe expanded and cooled, it did not do so smoothly. It underwent violent phase transitions, sudden shifts in its fundamental state, like steam condensing into water or water freezing solid into ice. Picture a vast lake freezing over on a cold night. As the water turns to ice, the new rigid structure cannot always match the old liquid one. Stresses build and the surface cracks with a loud snap. Theorists propose the universe did something similar during its first fractions of a second. During a pivotal shift known as the electroweak phase transition, the very forces of nature split apart. In that moment of cosmic reorganization, the fabric of spacetime itself might have developed flaws, topological defects. Think of them as cosmic cracks, one-dimensional strings or two-dimensional walls of concentrated energy. And just as a crack in a magnet creates new north and south poles, these defects in the cosmos could have spontaneously generated the first fundamental magnetic fields. This was not magnetism born from the motion of particles, but from the geometry of the universe as it snapped into a new reality. It was an inherent property written directly into the blueprint of everything, a fundamental signature left behind at one of creation's most critical junctures. That cosmic crackle of energy provided the initial spark, but it was the universe's next great act that truly broadcast its magnetic voice. The inflationary epoch was a moment of almost impossible transformation, a fraction of a second when the fabric of space itself expanded at a rate far beyond the speed of light. During this explosive growth spurt, the very quantum texture of the vacuum was not smooth. It frothed with tiny, temporary fluctuations, random pops of energy into existence. Among these quantum flickers were the faintest possible magnetic fields, ephemeral whispers born from the uncertainty that governs the smallest scales. As space inflated at an unimaginable rate, it did not simply get bigger. It stretched these quantum magnetic seeds, smoothing and amplifying them, pulling them from the microscopic world to a truly cosmic scope. Think of a single thread of spider silk, impossibly fine and short. Now imagine that thread being woven into a tapestry the size of a continent, its delicate pattern preserved and enlarged to cover an entire world. Inflation did precisely that to magnetism. It took a random, microscopic fluctuation and stretched it across the entire observable universe, weaving a faint, all-pervasive magnetic background into the cosmos. This process meant that by the time inflation ended, magnetism was not just a local phenomenon. It was a fundamental property of space itself, a fossil relic imprinted during the universe's most violent growth spurt. We often search for the echoes of inflation in the afterglow of the Big Bang, the cosmic microwave background, but its signature might also be written in the invisible magnetic fields that still thread the vast emptiness between galaxies. The universe did not just get bigger in that instant, it gained a magnetic soul, a silent, persistent force that would guide its evolution for billions of years. This magnetic soul, woven into the cosmos, would soon face its first great test against the universe's original voice. After the Big Bang, the cosmos was not silent. It was a roaring, dense fog of particles, a plasma where protons, neutrons, and particles of light were locked in a tight, frenzied embrace. In this hot soup, pressure waves surged outward. These were not mere vibrations but titanic sound waves, cosmic tsunamis that compressed and rarefied the primordial matter as they traveled. We call these ripples baryon acoustic oscillations, the very first sound waves to ever echo through the universe. And into this chaotic symphony, the primordial magnetic fields introduced a new and disruptive instrument. They exerted a subtle but persistent pressure, a magnetic pushback against the gravitational pull of the dense waves. Think of it like trying to create a perfect, concentric ripple in a pond while a steady, unseen wind is blowing across the surface. The wind does not stop the ripples, but it distorts their perfect shape, changing their spacing and their height. That is what magnetism did to those first cosmic sounds. It provided an additional force that altered the rhythm and the pattern of how matter ultimately clumped together in those early moments. The imprint of those sound waves is still visible today, frozen into the large-scale structure of the universe, a ghostly pattern in the distribution of galaxies. By mapping this fossilized echo with incredible precision, astronomers are searching for tiny, telltale anomalies in the pattern, a slight warping that could only be explained by the presence of those ancient magnetic fields. The universe's magnetic whisper may have left its signature on the very first note it ever heard. As the final echoes of that primordial sound faded, a profound silence fell across the cosmos. With the formation of the first neutral atoms, the universe had cleared its throat, allowing light to travel freely for the very first time, but there was nothing to see. This was the cosmic dark ages, an epoch of utter blackness stretching for millions of years. No stars pierced the void, no galaxies spun in the deep. The universe was a vast, featureless sea of cold, neutral hydrogen gas waiting. Yet within this profound stillness, an invisible hand was still at work. While gravity was the dominant pull, it was not the only sculptor. The primordial magnetic fields woven into the fabric of space during inflation and amplified by the dynamo remained. They were now one of the few active forces in this neutral darkness. These fields provided a subtle, pervasive pressure, a form of magnetic support that could push back against gravity's relentless tug. In some regions, this magnetic pressure acted like an invisible scaffold, preventing vast clouds of gas from collapsing under their own weight. In other areas, the fields became tangled and concentrated, actually enhancing the gravitational pull and accelerating the collapse. Think of a vast, flat plain of sand. Gravity wants to pull every grain to the lowest point, but an unseen network of fine wires just beneath the surface could cause the sand to pile up in some spots and remain flat in others. That is what magnetism was doing during the Dark Ages. It was not creating the structures itself, but it was dictating the pattern, establishing the preferred sites for future construction. The locations where the first stars would eventually ignite, the seeds of the first galaxies, were not chosen at random. They were selected by this silent, magnetic architect. The blueprints for everything we see in the luminous universe today, every brilliant galaxy and glittering star cluster, were drafted in the dark, guided by lines of magnetic force. While gravity and magnetism drafted the blueprints in the dark, a third, more subtle cosmic process was also at work, one that could build a magnetic field from absolute zero. This is the Biermann battery effect, a fundamental mechanism that allows order to emerge from pure chaos. In the swirling plasmas of the early universe, conditions were far from uniform. There were hills and valleys in the density of matter, regions of high pressure and low pressure. The Biermann battery ignites when these two gradients, pressure and density, find themselves out of sync. Picture a vast, hot sea where the temperature and the thickness of the water are constantly shifting. Now, imagine that the hottest, most energetic water is not in the densest, heaviest parts, but is instead spread unevenly across the map. This misalignment creates a natural dynamo. The charged particles in the plasma, pushed by pressure from the hot zones and pulled by density from the heavy ones, are forced into swirling, circular motions. And just as electrons moving through a copper wire generate a magnetic field, these swirling electric currents in the primordial plasma spontaneously created magnetism where none existed before. It was a cosmic battery, charging itself from the raw, disorganized energy of the young cosmos. This effect did not need a seed field to amplify. it could generate a magnetic whisper from the sheer chaotic structure of the universe itself. In the turbulent regions around the first clumps of matter, the very first density perturbations, countless such batteries were flickering to life. Each one was a tiny voice, adding its own unique magnetic signature to the growing chorus. This represents one of the most profound ideas in all of physics, that the universe has a built-in capacity to generate complexity and structure from initial disorder. The magnetic voice was not merely imprinted at the beginning. It was a song the cosmos learned to sing for itself, using the natural friction of its own uneven birth to create a new, guiding force from nothing. This silent magnetic architecture was punctuated by moments of violent transformation. Across the cosmic dark, magnetic field lines, stretched and twisted by the turbulent motions of the primordial plasma, would suddenly snap. This is magnetic reconnection, a fundamental process where opposing magnetic fields break and violently reconnect, releasing an enormous burst of stored energy in an instant. In the early universe, these events were the exclamation points in the ongoing magnetic narrative. Each reconnection converted the invisible tension of the magnetic fields into intense heat and powerful jets of accelerated particles. Imagine a vast tangled web of rubber bands stretched to their absolute limit. When one finally snaps, it does not just break quietly. It releases a sharp crack and a surge of energy, making the entire web shudder and rearrange itself. That is what reconnection did on a cosmic scale. This sudden injection of heat could have been a crucial factor in the Dark Ages, keeping pockets of hydrogen gas hot and ionized, preventing them from cooling and collapsing too quickly under gravity's pull. In other regions, the shock wave from a reconnection event might have had the opposite effect, acting as the final push that compressed a teetering gas cloud just enough to trigger its collapse into the very first stars. So magnetism was not just a silent guide, it was also an active participant. Its explosive punctuation marks directly influencing when and where the universe would finally switch on its lights. While reconnection events added explosive punctuation to the Dark Ages, another, more patient process was weaving magnetism into the very foundations of cosmic structure. This is the Harrison mechanism, a concept that ties the birth of magnetic fields directly to the gravitational ripples that would one day form galaxies. During the universe's radiation-dominated youth, the cosmos was not a smooth, uniform fluid. It was rippling with tiny density fluctuations, regions where matter was ever so slightly more packed together. These are the same primordial imperfections that gravity would later amplify into the vast cosmic web of galaxies and clusters. The Harrison mechanism reveals that these same density hills and valleys could also generate rotation. As these over-dense regions pulled in matter from their surroundings under gravity's influence, they did not always pull evenly. The inflows of plasma could become skewed, creating a natural swirl or vorticity. Picture a river flowing around a bend. The water on the outside of the bend moves faster than the water on the inside, and this difference in speed creates a swirling current, a whirlpool. In the early universe, the uneven gravitational pull of a density fluctuation acted like that river bend, setting the cosmic plasma into a slow, deliberate spin. And just as the Biermann battery relied on misaligned pressures, this organized swirling motion of charged particles automatically generated a magnetic field. It was a direct conversion, gravity's pull creating a whirl, and that whirl generating a magnetic whisper. This process makes magnetism an inseparable partner to gravity in the story of structure formation. The very same seed, the same tiny lump in the density of the universe, was destined to become both a galaxy and the source of its own magnetic field. This suggests that magnetism is not a later addition or a cosmic afterthought. It was encoded into the blueprint for everything from the very first moment gravity began to draw its designs in the dark. This silent tug of war between gravity and magnetism defined the first chapters of cosmic structure. Gravity was the undeniable heavyweight, the great attractor relentlessly pulling matter into its embrace. Yet magnetism offered a subtle but widespread form of support, a persistent pressure pushing back against collapse. In regions where the primordial magnetic fields were particularly strong, they created magnetic cushions, effectively propping up vast clouds of gas against their own weight. Imagine a dense, dark cloud of hydrogen slowly succumbing to gravity's inward pull. Just as it is about to cross the threshold of collapse, it encounters this invisible, springy barrier. The cloud presses down, but the magnetic pressure pushes back, delaying the final plunge. This resistance was not about stopping gravity forever, but about controlling the timing and the scale of the collapse. It acted as a cosmic filter, determining which gas clouds were truly destined to become stars and which were not yet ready. This delicate balance had a profound consequence. It helped set the characteristic mass scale for the very first stars and protogalaxies. Without magnetic support, gravity might have pulled matter into a chaotic assortment of structures, from tiny, fleeting clumps to monstrous, unstable behemoths. But with magnetism in the mix, the collapse was more regulated. The magnetic fields essentially set a minimum size, a cosmic quota for a collapsing cloud. They prevented the smallest, most fragile structures from forming too quickly, ensuring that when stars finally did ignite, they did so with a certain grandeur and stability. The outcome of this universe-wide competition, this invisible negotiation between two fundamental forces, was literally written into the initial mass function of stars. That statistical distribution, which astronomers still measure today, carries the faint signature of magnetism's early resistance. The first structures to light up the cosmos were not born from gravity's pull alone. They were the children of a delicate compromise, forged in the dark between an unstoppable force and an invisible, persistent shield. Yet another, even more profound, principle was also at work in that seething dawn. Deep within the quantum frenzy of the newborn cosmos, a subtle asymmetry might have powered the universe's magnetic voice. This is the chiral magnetic effect, a phenomenon that connects the world of the impossibly small directly to the vast, structured cosmos we see today. Chirality is a concept of handedness. Think of your own two hands. They are mirror images of each other, but you cannot perfectly superimpose one upon the other. In the same way, the most fundamental particles in the universe can be left-handed or right-handed, a property describing the direction of their spin relative to their motion. Under normal conditions, the universe maintains a perfect balance between these two versions, but in the extreme heat and density of the very first moments, this balance could have been broken. A slight excess of, say, left-handed particles over right-handed ones could have emerged. Now, place this imbalance within a magnetic field, even a weak primordial one. Something remarkable happens. The left-handed and right-handed particles will respond differently to the field's influence, and this difference causes them to separate. This segregation of charge creates a flow, an electric current circulating along the lines of the magnetic field. And as any physics student knows, an electric current itself generates its own magnetic field. Here lies the magic of the chiral magnetic effect. It creates a self-sustaining loop. An initial magnetic field causes an imbalance of chiral particles to generate a current, and that current then amplifies and reinforces the original magnetic field. It is a quantum dynamo, a self-powering engine that could have operated when the universe was less than a second old. This suggests that the cosmos did not just stumble upon magnetism. Its voice may be an inevitable consequence of the most fundamental laws of particle physics, a song written into the quantum code of reality itself. The faint magnetic fields we infer between galaxies today could be the vastly stretched and diluted echoes of a quantum whisper from the first instant of time. That silent, magnetic conversation from the Dark Ages left a permanent record. To read it, we must look at the oldest photograph ever taken, the cosmic microwave background. This faint afterglow is the light released when the universe first became transparent, a snapshot frozen in time just 380,000 years after the Big Bang. It is a baby picture of the cosmos, and etched into its subtle patterns could be the signature of those primordial magnetic fields. How could an invisible force leave a mark on light? The fields would have influenced the way that primordial light scattered off the hot plasma. This interaction could have imprinted a specific, telltale twist on the light's polarization, a particular direction in its vibrations. It would be a faint, ghostly spiral pattern woven into the fabric of the background radiation itself. These fields would also have gently warmed the cosmic plasma in certain regions, creating minuscule hotspots in the temperature map that gravity alone cannot explain. Finding these distortions is one of the greatest challenges in modern cosmology. The signals are incredibly faint, buried under eons of cosmic noise and later interference. Yet our most powerful observatories are now hunting for them with relentless precision. Missions like the Simons Observatory and the next-generation CMB-S4 project are essentially ultra-sensitive magnetic detectives, scanning the cosmic background for these vanishingly small anomalies. To discover the magnetic fingerprint in the CMB would be a monumental achievement. It would be like uncovering the first recorded words of the cosmos, a direct message from an era before stars, before galaxies, when the universe spoke only in the language of magnetism. These cosmic rays are not just random streaks of energy. They are messengers carrying encrypted information about the vast distances they have crossed. When a proton or an atomic nucleus is accelerated to nearly the speed of light, becoming a cosmic ray, it does not travel in a straight line. The moment it encounters a magnetic field, however faint, its path curves. It begins to spiral, tracing a corkscrew pattern along the invisible lines of magnetic force that permeate the cosmos. For the highest energy cosmic rays, those with energies millions of times greater than anything produced in our largest particle colliders, this deflection is a critical clue. Their immense energy makes them somewhat more resistant to being thrown off course, but they are still swayed by the largest and most coherent magnetic fields they encounter. If the early universe was laced with a widespread primordial magnetic web, then the very first cosmic rays, perhaps generated by the explosive deaths of the earliest stars, would have had their journeys dramatically altered. Their paths would have been scrambled, their origins obscured by a cosmic maze of magnetic mirrors and lenses. When we look at the sky map of these ultra-high-energy cosmic rays today, we do not see them pointing back to their sources. Instead, we see a surprisingly uniform, almost random distribution. This isotropy, this lack of a clear direction, is itself powerful evidence. It suggests that something has been twisting their trajectories across billions of light years. That something is most likely a diffuse, intergalactic magnetic field, a fossil relic from the dawn of time that still acts as a grand conductor for these energetic particles. By analyzing the precise patterns in their arrival, the subtle clustering or the lack thereof, and by measuring their energy spectrum, we can work backwards. We can use the cosmic rays themselves as probes to chart the strength and the structure of the magnetic fields they have traveled through. It is an astronomical form of triangulation, using a hail of high-energy particles to map the invisible architecture of the universe. These particles are our only direct sampling of the vast, empty spaces between galaxies, and they tell us that those voids are not truly empty. They are threaded with the faint, enduring lines of a magnetic field that has guided cosmic traffic since the beginning. That final, critical push to ignite the first stars required a cosmic solution to a fundamental problem. As vast clouds of primordial gas succumbed to gravity, they did not fall inward smoothly. They began to spin, and like a figure skater pulling in her arms, this spin accelerated as the cloud contracted. This buildup of angular momentum created a powerful centrifugal force, threatening to halt the collapse long before the core became hot and dense enough for nuclear fusion to begin. The universe's first light was in danger of being stillborn, trapped in a whirl of its own making. Magnetic fields provided the essential break. The lines of magnetic force, frozen into the collapsing gas, were stretched and wound into a tight, rotating spiral. This created a magnetic slingshot effect, flinging material outward from the cloud's equator and carrying the excess spin away with it. This process, known as magnetic braking, systematically drained the cloud of its rotational energy, allowing the heart of the protostar to continue its inward plunge. Without this mechanism, the first stars might have torn themselves apart or settled into vast, dark, spinning disks, never achieving the critical density for ignition. The properties of these first stars, known as population 3 stars, were likely sculpted by this magnetic influence. Their immense size, their potentially rapid rotation, and even their ultimate fates in supernova explosions were all shaped by how efficiently magnetic fields managed the collapse. So the very first pinpricks of light that ended the cosmic dark ages did not simply switch on. They were kindled, their fusion engines sparked by the release of magnetic tension. The universe's first voice did not just guide the construction of its first lanterns. It provided the final, crucial turn of the key that brought them to life. This chaotic magnetic symphony required a final, organizing principle to truly sculpt the cosmos. The early universe was a cauldron of Magneto-hydrodynamic turbulence, a state where magnetic fields and fluid motion became a single, inseparable entity. The entire primordial plasma was not just a fluid with a magnetic field passing through it. The field was frozen into the fluid, and the fluid's motion dictated the field's shape, which in turn guided the fluid's flow. They were locked in a frenetic, codependent dance. This turbulence was not random noise. It was a powerful, self-organizing engine that transferred colossal amounts of energy from the largest scales down to the very smallest. Picture a vast, stormy ocean. A massive wave born from a distant storm does not simply travel intact until it crashes on a shore. It breaks down, transferring its energy into smaller waves, then into choppy whitecaps, and finally into a fine, chaotic mist that dissipates as heat. This cascade is precisely what happened in the primordial plasma, but with magnetic fields woven into every step. As large-scale eddies of magnetized plasma twisted and collided, they shattered into smaller, faster-moving whirlpools. This process continued, cascading energy down through ever-diminishing scales. At the very smallest levels, this turbulent energy did not simply vanish. It was dissipated, converted into heat through the relentless friction and reconnection of magnetic field lines. This provided a crucial, widespread heating mechanism for the intergalactic gas during the Dark Ages, keeping it warm and partially ionized long after the cosmic microwave background had faded. This turbulent dance did more than just heat the gas. It stirred the cosmic pot with immense efficiency, mixing and churning the primordial elements, ensuring that the building blocks for future stars and galaxies were evenly distributed. The locations where galaxies would eventually condense were not passive sites of accumulation. They were dynamic cauldrons that had been vigorously stirred by this Magneto-hydrodynamic turbulence for hundreds of millions of years. The final structure of the cosmic web, the vast filamentary network of galaxies we see today, carries the ghostly imprint of this ancient, chaotic, and fundamentally magnetic whirlwind. The magnetic fields we observe today are not recent inventions. They are ancient relics. Look at any grand spiral galaxy, its arms traced by stars and dust. Woven through that majestic structure is a vast, coherent magnetic field, often aligned with the spiral arms themselves. These are not random, localized phenomena. They are galactic-scale forces, and their origin points back to the very beginning. A leading theory suggests these are fossil fields, amplified remnants of the primordial seeds we have been discussing. When a proto-galactic cloud first began to collapse out of the cosmic dark ages, it did not just pull in gas and dark matter. It also captured the magnetic field lines that were already present in that region of space. Think of a fisherman casting a wide net into the sea. The net captures not just the water, but everything suspended within it. In the same way, the collapsing cloud ensnared the faint, all-pervasive magnetic whispers of the early universe. This captured field was then subjected to an immense cosmic workout. As the galaxy formed and its disk began to rotate, a powerful dynamo ignited. The sheer motion of the conductive gas, swirling in differential rotation, acted like a trillion generators all working in concert. This galactic dynamo took that faint primordial seed and amplified it exponentially over billions of years, twisting and winding it into the organized, large-scale field we detect today. If this theory is correct, then the magnetic field you would measure in a distant spiral galaxy is not merely a local feature. It is a direct descendant of the universe's first magnetic utterances. The faint hum that echoed through the plasma before the first stars now resonates as a powerful chord in the galactic orchestra. It is a living fossil, a force that has been preserved, nurtured, and amplified across almost the entire history of cosmic time. But the universe's magnetic story may hinge on a missing character, a particle that has never been seen. According to our most ambitious theories of how the fundamental forces unite, the scorching dawn of the cosmos should have been filled with magnetic monopoles. Unlike every magnet we have ever encountered, which always has both a north and a south pole, a monopole would be a pure, isolated pole, a solitary north or a lone south wandering through the primordial plasma. These particles are not just a curiosity, they are predicted relics from an era of perfect symmetry, when the electromagnetic, weak and strong forces were all one and the same. As the universe cooled and this perfect symmetry broke, it should have left behind topological defects, and monopoles are one of the most prominent examples. Their existence would have been a fundamental feature of the newborn cosmos, and their motion would have been electric. Picture a sea of these isolated north poles, all repelling each other with immense force, scattering through the plasma like charged particles. Every time a moving electric charge creates a magnetic field, a moving magnetic charge, a monopole, would create an electric field. This swirling interplay between electric and magnetic fields, driven by a sea of these exotic particles, could have generated the first substantial cosmic magnetic fields. The sheer density and motion of monopoles could have acted as a powerful primordial battery, jump-starting the universe's magnetic landscape in an instant. This is why the decades-long, elusive hunt for a magnetic monopole is about so much more than finding a new particle. It is a direct search for a potential architect of cosmic magnetism. If monopoles were real, and if they were abundant in that first moment, then the faint magnetic fields we infer across the universe today could be the faded echo of their frantic, symmetric dance. Their confirmed absence, however, tells its own profound story, forcing our theories of the universe's very first moments to rewrite themselves, eliminating the very conditions that would have made monopoles commonplace. That final, crucial ignition of the first stars did not simply light up the darkness. It began a cosmic war of attrition against the pervasive neutral hydrogen fog. This was the epoch of reionization, a billion-year struggle where the universe fought to become transparent. And in this pivotal battle, the ancient magnetic fields served as both strategist and weapon. As the first proto-galaxies collapsed, their internal magnetic fields, amplified from primordial seeds, dictated the very architecture of their birth. They influenced how gas fragmented and collapsed, determining the size and distribution of those first, brilliant stellar nurseries. A galaxy born with a strong, organized magnetic field was not a chaotic firestorm. It was a structured entity, its internal dynamics shaped by invisible lines of force. This structure was critical for the next step, the escape of the very radiation that would clear the cosmic fog. The first stars and quasars blasted out intense ultraviolet light, the kind of energy needed to rip electrons away from hydrogen atoms, reionizing the gas. But for this radiation to reach the vast intergalactic medium, it had to first escape its own galactic cradle. Dense walls of neutral hydrogen within the galaxy could easily absorb these photons, trapping the light. This is where magnetism played its subtle, guiding role. Powerful magnetic fields can channel and collimate intense radiation and plasma, funneling them into focused jets that punch through the densest galactic material. Think of a lighthouse whose beam is concentrated by a complex series of lenses, allowing it to cut through the thickest sea fog, rather than a bare bulb that simply illuminates its immediate surroundings. Magnetic fields acted as those cosmic lenses, helping to drill clear pathways through the neutral gas, enabling the first ultraviolet radiation to stream out into the void. This magnetic assistance meant that the process of reionization was not a uniform, slow brightening. It was a patchy, structured clearing, advancing along the magnetic highways that had been laid down in the darkness eons before. The ancient magnetic whisper helped to orchestrate the final act of cosmic dawn, systematically burning away the last vestiges of the primordial fog to create the brilliant, transparent universe we are privileged to observe today. These vast cosmic voids are not the empty deserts they appear to be, stretching for millions of light years between the glittering filaments of the cosmic web. These regions contain almost no galaxies, only the most tenuous traces of ionized gas. Yet even here, in the deepest emptiness, the universe's magnetic voice still speaks. Astronomers have found compelling evidence that these intergalactic spaces are threaded with magnetic fields. Their strength is almost unimaginably feeble, 1 trillion times weaker than Earth's own magnetic field, but their mere existence is a profound cosmological clue. The presence of magnetism in the void presents a fundamental question. Where did it come from? There are two compelling and competing origin stories for these intergalactic fields. The first possibility is that they are truly primordial, the direct descendants of those initial seeds generated during inflation or phase transitions. In this scenario, the expansion of the universe itself has stretched these fields to truly cosmic proportions, thinning them out but preserving their coherence across mind-boggling scales. They would be a fossil, perfectly preserved from the universe's first moments. The second possibility is that they are pollution on a cosmic scale. Over billions of years, galaxies have been anything but quiet neighbors. Supernova explosions, quasar jets, and powerful galactic winds have blown colossal streams of magnetized material out of galaxies and deep into intergalactic space. This magnetic exhaust could have slowly filled the voids, a kind of cosmic smog that has gradually accumulated. How can we possibly tell the difference between a primordial fossil and galactic pollution? The answer lies in the geometry of the field itself. A truly primordial field, stretched by the universe's expansion, would be incredibly ordered. Its lines of force would be coherent, showing a preferred direction over vast intergalactic distances. It would be a smooth, cosmic background hum. A field blown out from galaxies, however, would be chaotic and tangled, a messy web of magnetic spaghetti with no large-scale order, reflecting the violent and unpredictable nature of its birth. By studying how these fields affect the light from distant quasars and the paths of ultra-high-energy cosmic rays, we are essentially performing a cosmic archaeological dig. We are sifting through the evidence to see if the magnetic field in the void is a pristine relic from the beginning, or the accumulated exhaust from trillions of stellar engines. The answer will tell us if we are hearing the universe's first words or merely the distant, recycled echo of its later, more boisterous life. Cosmologists are now running the universe in reverse. They build digital twins of the cosmos inside some of the world's most powerful supercomputers, and for the first time, these virtual universes are being born with magnetism woven into their very code. These are not simple models. They are breathtakingly complex simulations that track the interplay of dark matter, gas, and magnetic fields across billions of light years and from the first instant to the present day. We can watch as a faint, all-pervasive seed field, a ghost from inflation, is caught in the whirlpool of a collapsing protogalaxy. We see the Dynamo effect ignite, twisting and amplifying that faint whisper into a structured, powerful force. The simulations reveal how these magnetic fields act as a subtle pressure, shaping the flow of gas along the filaments of the cosmic web, determining where the first stars will burst into life and how galaxies will ultimately spin. It is like having a time machine for cosmic forces, allowing us to witness the invisible architecture of creation as it unfolds. But these digital universes are more than just a spectacular show. They are a crucial testing ground. Scientists run multiple simulations, each starting with a different theory of magnetogenesis. One universe might begin with magnetic fields born from quantum fluctuations during inflation. Another might rely solely on the Biermann battery effect, generating fields from chaos later on. Then comes the critical step, the moment of truth. The researchers compare the final structure of their simulated universe, its pattern of galaxies and the magnetic fields within them, against our actual maps of the real cosmos. Does the simulated magnetic web match the faint field we detect in the voids? Do the galaxies in the simulation have the same magnetic strengths and configurations as the ones we observe? If a simulation that starts with a primordial seed field produces a universe that looks remarkably like our own, it is a powerful vote of confidence for that theory. We are essentially replaying the tape of cosmic history over and over, with different initial conditions to see which version of the magnetic dawn leads to the world we see outside our window tonight. That faint twist in the light of distant quasars may be our most direct line to the cosmic dawn. As this polarized light journeys for billions of years across the void, it passes through vast, invisible oceans of magnetized plasma. Each encounter leaves a subtle mark, a slow, steady rotation of the light's polarization plane, a phenomenon known as Faraday rotation. The amount of this rotation is a precise scientific code. It tells astronomers the strength of the magnetic fields the light has passed through and the density of the electrons it has encountered along its immense journey. By observing thousands of these distant cosmic beacons, we can effectively perform a magnetic tomography of the universe, charting the invisible fields woven through the cosmic web's great filaments and empty voids. The critical clue lies in the pattern of these rotations across the entire sky. If we were only mapping fields from nearby galaxies or clusters, the signal would be a chaotic patchwork, a testament to local and recent magnetic activity. But if we were to detect a consistent, all-sky background of Faraday rotation, a uniform whisper that persists no matter which direction we look, it would point to something far more profound. Such a universal signal would be the signature of a primordial magnetic field, a fossil relic stretched across the entirety of space. It would be the enduring imprint of those first magnetic conversations, a ghostly fingerprint left on every photon that journeys through the cosmos. Finding this signal is like trying to hear a single, steady note held within a roaring symphony. It requires sifting through the light from countless quasars, subtracting the local magnetic noise of galaxies and clusters, and searching for what remains. That residual hum, if it exists, would be the direct voice of the infant universe, a magnetic echo that has traveled since the beginning, still twisting the light that reaches our telescopes today. But the magnetic story of the cosmos may be intertwined with its greatest unsolved mystery. We have followed the influence of magnetism through the luminous matter we can see, the stars and galaxies made of protons, neutrons, and electrons. Yet all of that accounts for less than 20% of the universe's total matter. The rest is the enigmatic presence of dark matter, an invisible substance that reveals itself only through its gravitational pull. Could these two cosmic narratives, magnetism and dark matter, be secretly connected? It is a highly speculative idea, but one that theorists are beginning to explore with serious curiosity. What if dark matter is not completely dark to magnetic forces? Certain theoretical models propose that some dark matter particles could carry a tiny fractional electric charge or possess their own unique form of magnetic moment. This would mean that as these unseen particles swirled and clumped in the early universe, their motion could have generated faint magnetic fields of their own. In this scenario, dark matter would not just be a passive gravitational scaffold. It would have been an active participant in the universe's magnetic dawn, its invisible hands helping to weave the very magnetic fabric that would later guide the birth of stars. Alternatively, the connection could be more indirect. The gravitational influence of dark matter is what drew the first structures together. This process, the violent clustering and merging of dark matter halos, would have stirred the primordial plasma with immense force. That turbulent motion could have acted as a colossal battery, powerfully amplifying any pre-existing magnetic seeds through mechanisms like the Biermann battery or the Harrison mechanism. In this version, dark matter provides the kinetic energy, the raw power for the cosmic dynamo. The implications of such a link are staggering. It would mean that the two most profound puzzles in modern cosmology are not separate. The quest to understand the invisible 85% of the universe's matter and the search for the origin of cosmic magnetism could be two sides of the same coin. Discovering the fundamental nature of dark matter might finally explain how the magnetic fields that thread through galaxies first came to be, and conversely, by precisely mapping the geometry and strength of the most ancient magnetic fields we can find, we might uncover crucial clues about the properties and behavior of dark matter itself. This potential unity suggests that the forces which shaped our cosmos are even more deeply interwoven than we ever suspected, a single, elegant tapestry woven from both light and shadow. This search for the universe's first words is pushing our technology to its absolute limits. We are building ears sensitive enough to hear a whisper across 13.8 billion years. The next generation of observatories, like the Square Kilometre Array, represents a quantum leap in this quest. This is not a single telescope, but a vast network of radio dishes spread across 2 continents, functioning as one colossal instrument with a collecting area of, as the name implies, a square kilometer. Its unprecedented sensitivity will allow it to map the cosmic web in stunning detail, tracing the faint, magnetized plasma in the filaments between galaxies. It will search for the subtle distortions in radio waves from distant quasars, looking for that all-sky Faraday rotation signal that would be the smoking gun for a primordial field. At the same time, a new wave of cosmic microwave background experiments is being designed with one primary goal: to find the unique spiral pattern in the CMB's polarization that could only have been etched by primordial magnetism. We are entering an era where these instruments will not just see the universe, they will listen to its magnetic soul. The data they gather will be so immense and so precise that it could finally settle the great debate, distinguishing between a primordial fossil and galactic pollution. We stand on the verge of a transformative moment, a point where the theoretical becomes tangible. The first magnetic words of the cosmos, spoken long before light could travel, may soon be translated directly from the sky, rewriting our fundamental story of how everything began. This makes primordial magnetism a unique kind of cosmic fossil. Light from the cosmic microwave background gives us a spectacular snapshot, a single moment frozen in time when the universe became transparent. But that picture was taken when the cosmos was already 380,000 years old, a toddler in cosmic terms. Magnetic fields offer something far more ancient. They are not a snapshot but a continuous recording, a relic that has persisted from a potentially much earlier epoch, carrying information unscathed through the fiery plasma of the universe's first moments. They could hold direct clues about the violent inflation that stretched space-time, or the dramatic phase transitions that forged the fundamental forces as we know them. Studying these fields is not like astronomy, it is cosmic paleontology. We are not just looking at a picture of the infant universe, we are digging for its very bones, the oldest surviving structures in all of existence, hoping to piece together the anatomy of creation itself from the faint magnetic whispers that have endured for every single second of cosmic history. This silent, magnetic dawn forces us to rewrite the very definition of a living cosmos. We have long pictured the universe's infancy as a dark and passive void, a quiet stage waiting for the grand entrance of starlight. But the presence of a guiding magnetic force shatters that image entirely. It reveals a cosmos that was never truly asleep, but was instead a hive of invisible activity, buzzing with a fundamental intelligence long before the first star flickered. The Dark Ages were not an empty intermission. They were a period of intense, hidden construction where the blueprints for galaxies were drafted not in light, but in lines of force. This transforms our understanding of cosmic evolution from a simple story of light, switching onto a far richer narrative of an unseen architecture steadily emerging from the chaos. It suggests that the universe's most fundamental creative work was done in the dark, guided by a hand we are only now learning to perceive. What does it mean for our place in the cosmos if the void itself was already structured and speaking a complex language before life, or even worlds, were possible? This magnetic origin story implies that the tendency for order, for structure, for conversation, is woven into the deepest fabric of reality. We are not the result of a universe that stumbled into complexity. We are the heirs to a cosmos that was always, from its very first breath, striving to build. Our journey reveals a cosmos whose first language was not light, but the silent, persistent grammar of magnetism. Long before any star could blaze, this invisible force was already at work, drawing the blueprints for galaxies in the dark. It guided the collapse of the first gas clouds, braked their furious spins, and even helped them finally ignite, turning the cosmic dark ages into a dawn. The brilliant tapestry of stars we see today is the magnificent outcome of that ancient, hidden conversation. As our most powerful telescopes now hunt for the faintest echoes of these primordial fields, we are doing more than just studying astrophysics. We are learning to read the very first words of creation, a story written in lines of force across the void. So the next time you gaze up at the night sky, see it not merely as a collection of distant lights. See it as the final, luminous verse in a poem that began with a magnetic whisper, a cosmic narrative that started its telling long before the universe ever thought to switch on its lights. What do you think these ancient magnetic whispers are telling us about our place in this grand story? Share your thoughts in the comments and subscribe for more journeys to the very edge of understanding.